All right, so now we're going to take a look, just a brief look at probably one of the more important tools in chemistry, which is called the periodic table. Um, we're going to just do a quick cursory look at the periodic table now. We'll talk more about some of the characteristics and other information that we can extract from it a little bit later on. Before we get to this, though, I just wanted to remind ourselves of a couple things that we'll use to help us describe the periodic table. So remember we talked about John Dalton and his atomic theory that we used to describe the atom and everything else. So there were several other parts of that theory that we didn't quite get to. So let's review what he actually said back in 1804. So he said that all matter, so everything around us and in us, is composed of these really, really tiny particles called atoms, and we explored atoms in some detail. What he also said was that atoms cannot be subdivided, created, or destroyed. Now, obviously, this has since been proven to be false because there are actually now subatomic particles that we know about. So protons, neutrons, electrons, etc. And those are really important. They help describe the characteristic of our atom. So even though Dalton proposed this way back when, this was a couple hundred years ago, this has since been updated. He also said that atoms of a given element are all identical in size, mass, and other properties. Now, we've also found this not to be entirely true because we just talked about isotopes. So actually, they can be different. So atoms of a particular element can be different from each other, right? Specifically isotopes of the same element, but they have different numbers of neutrons. He also said that atoms of different elements differ in size, mass, and other properties, and that's going to be critical for when we look at all the elements in the periodic table. He also said that atoms of different elements can combine in whole number ratios to form chemical compounds. So for example, two hydrogens can combine with one oxygen in a whole number ratio to form H2O, and that's our compound called water. And then he also said that in a chemical reaction, so in chemical reactions, atoms get rearranged, they get recombined, or they can be separated from other atoms. So we make new things, in other words, in a chemical reaction. But the atoms are neither created nor destroyed. And that's part of a very important law in chemistry called the law of conservation of matter, right? So matter can neither be created nor destroyed, is how we would state that. But it can be converted from one form to another. So Dalton proposed the atomic theory way back when, right? Some of it still holds true today, but parts of it we have since known, we've since updated based on new discoveries. So as people were describing, or not describing, as people were discovering more and more atoms, as time went by, naturally the inclination was to organize these different elements. And there were several attempts at organizing the elements. One of the earlier successful attempts at organizing the elements was by a scientist called Mendeleev. Okay, and Mendeleev organized the elements in a systematic way. He organized them by increasing atomic mass. And what he found was that when he organized the elements this particular way, he found that there were repeating characteristics. Or properties of the elements. In other words, certain characteristics would, as you increase the elements, from small mass to a large mass, you would have a certain set of characteristics that he would observe, and then those characteristics would repeat themselves in maybe another set of increasing atomic masses. So we refer to these as periodic properties. Okay, as an analogy, you can think of in a grandfather clock, the pendulum that swings back and forth. That's a periodic motion as well. Properties change that way. And that's what Mendeleev discovered. Now, the periodic table we use today is not organized by increasing atomic mass. Instead, today, periodic table is organized by increasing atomic number. And we still see those periodic patterns. Right, so increasing atomic number, which is, again, atomic number is just the number of protons. So when the elements are arranged this way, we see these periodic properties. Now, one of the things about Mendeleev and his organization of the elements is that there were gaps because not all the elements had been discovered yet. He actually had spaces in his table where elements were supposed to be. He didn't know what those elements were at the time, but he was able to predict the properties of those elements. And that is one of the key characteristics of even the periodic table today, is that it was very predictive, right? Just based on where something is on the periodic table, you can actually say a lot about its characteristics and its properties. So the table that we see today, and this is a copy of one that's from your textbook, this is color-coded. The periodic table that you will get to use on an exam or a quiz, for instance, would be the ones that I've been referencing all along so far. So let me bring this down here. So this would be the periodic table that you're going to be provided with. So it's black and white. It isn't color-coded, and there's not a ton of information on there, but there's enough information that you can use. So periodic table, just a way to organize all 118 elements that are known. And when we organize a periodic table this way, what we actually find is that there are a couple ways by which we can approach and take a look at the elements. So what we find is that we can separate the table into two general categories. We have what are known as groups. We have what are known as periods on the periodic table. Okay, those are the first two ways that we're going to take a look at our table. So groups, take a look at groups first. Groups are sometimes called, these are columns on the periodic table, or families. Okay, and what we would see then, again, just due to the organization, members or elements of the same group have similar characteristics or similar properties. Okay, so the groups, these are columns on the periodic table. So for example, if I look at the table here and I highlight, let me actually use, yeah, we'll use this one. So the first group, or the first column, would be this one here, highlighted in yellow. Okay, that's group 1. This would be group 2. Do a different color. So that's group 1. This would be group 2. Group 3, we consider this one over here. You jump all the way over across. This is group 4, group 5, 6, 7, and 8. So you'll notice on this particular periodic table, there are a couple numbering systems that look a little different. What we're going to focus on is the A numbering system. Okay, so group 1A is this, all the way down, okay, from top to bottom. That's group 1A. Group 2A is this column. Group 3A is all the way over here. Group 4A is this one. 5A, 6A, 7A, and then 8A. Okay, so what we're saying then is that members of, or elements in the same group have similar characteristics. So we can say, for instance, that if I pick a couple elements in group 7A, So fluorine and chlorine, we would predict those two to have similar characteristics. We would predict sodium and potassium in group 1A to have similar characteristics. Okay. All of these groups here in the middle, we kind of collectively refer to these as by a different term, and we'll talk about that in a little bit. So those are groups. Periods, though, are the horizontal rows in the periodic table. So the first period, period 1, would be this row here. So it starts with hydrogen, goes all the way across to He, helium. That's the first period. Second period, period 2, would be lithium, beryllium, all the way across to neon. That's period 2. Period 3, so third period, would be sodium, magnesium, all the way across to argon, and so on and so forth. Okay, so periods are horizontal rows. Groups are the vertical columns on the periodic table. And what they found, and again by organizing the elements by increasing atomic number, is that as you go across a period, the characteristics of the elements change in a predictable way. Okay, so we said before that in a group, okay, remember elements in the same group have similar characteristics. Elements in the same period are going to have different characteristics, but they differ in the same way. So going across group period 2, for example, from left to right, as you go across that period, the characteristics of the elements change, and they change in the same way as if I go across period 3, right? So that's a repeating pattern or a periodic pattern. And that's what we mean by periodic in terms of the table. So we can organize the periodic table in terms of groups and elements. Groups and periods. We can use those to identify where elements are located on the table. So for example, an element in group 3A and period 3 is, so we look at our periodic table, we find group 3A, that's this group. So right away we know it can only be one of these elements. And the third period, period 3, going all the way across. So where these two intersect would be right here. So that would be aluminum, Al. Okay, so you can use the groups and periods as sort of coordinates for the location of the atoms in the periodic table. There's some broader organizational terms that we use to classify the elements on the table. We have what are known as metals. We have non-metals, and then we have what are known as metalloids. Okay, so metals make up the vast majority of the elements on the periodic table, right? They're everything here highlighted in blue. And metals tend to be good conductors of heat and electricity, and they make up the majority of the periodic table. We'll abbreviate periodic table as PT from this point onwards. And metals are generally found on the left side of the periodic table. Non-metals, in contrast to metals, are poor conductors of heat and electricity, and they are found on the right side generally of the periodic table. Okay, so we have everything here that's highlighted in green. And then you'll notice there's one that kind of sticks out, hydrogen over on the left side. So generally they're found on the right side of the table, and then in between the metals and the non-metals, we have what are known as metalloids. Again, these are highlighted here in orange. They kind of form that zigzag line or that staircase as you go across the periodic table. And these are going to have intermediate properties kind of in between the metals and the non-metal. So for example, instead of being good conductors of heat and electricity or poor conductors of heat or electricity, these tend to be semiconductors. Again, a good example of that would be silicon, Si, which is found in a whole host of electronic devices. Metalloid, sometimes you'll see the term semi-metals. You don't see it as often, but you might encounter it in your readings or if you look online. All right, so we have our groups, we have our periods, we have metals versus non-metals versus metalloids. So we talked about these vertical columns or groups before. There are special names that we give to some of the groups. So for example, the elements in group 1A are known as alkali metals. Okay, so group 1A, these are called alkali metals. So lithium, sodium, potassium, rubidium, cesium, and francium. It's group 1A. Group 2A, the group right next to it, these are known as alkaline earth metals. Okay, and these terms mean something very specific, which we'll see later on. If we jump over now to group 6A, so things like oxygen, sulfur, selenium, tellurium, polonium, these are known as chalcogens, which is a term you don't see very often, but it is, you do encounter it sporadically. The group next to them, group 7A, these are known as halogens, or halogens, if you want to pronounce it differently. It's both spelled the same. And then the very last group, group 8A. Okay, so again, we're using the A numbering system. These are known as the noble, not Nobel, not Nobel, but noble, Noble, the noble gases, or sometimes they're called inert gases. And inert there means unreactive. So we need to know those collective names given to those specific groups on the periodic table. So we did talk also about the fact that the very middle portion of the table, that these are numbered here with the B numbering system, we collectively refer to these as transition metals or transition elements. And then you're probably wondering, we didn't really talk about any of this part of the table before, but there are two rows that are kind of down here on their own and at the bottom, right? These are known as inner transition elements. And if you look at the atomic numbers associated here, in this first row of the inner transition elements, it goes from 58 cerium all the way over to 71 lutetium. And then the second row goes from 90 thorium all the way over to 103 lawrencium. So, and if you look at the transition elements, you see that it jumps from 57 lanthanum to 72 hafnium. So where's 58 to 71? Well, there it is, right here. And then it goes from actinium, 89, to 104, rutherfordium. Where's the 90 through 103? Well, it's here. So these would naturally belong in here, but if we stuck them in, it would make the table a little too wide and a lot more cumbersome to work with. So we just take them out, put them on the bottom, we call them the inner transition elements, but that's where they would normally belong, in this region here. So as you look at the periodic table, and again, we're going to extract way more information down the road, but as of right now, this is just how we interpret the groups, the periods, the different names for the groups, the different regions of the table. we need to be familiar with the terms.